Hi, today we're going to talk about total change, area under the curve, and the definite integral. So let's say that we're given a formula for a car's velocity, say in meters per second, as a function of time. So we're going to let v of t equal t squared for t equals 0 to t equals 3. The question we ask ourselves is how far did the car travel? So we know that the car's speed or velocity is changing with every instant, so it's not going a constant speed at any time. So we can't find the exact distance doing anything that we might already know about distance and velocity and time. But what we can do is we can find an approximation of the distance traveled by the car, because we know that distance equals velocity times time. But again, our velocity isn't constant. So the best we can do is approximate the distance or approximate the velocity for certain subintervals. So we could divide the time from 0 to 3 into every second or every half second or every quarter of a second or whatever subinterval you'd like to do. And then we can choose a velocity for each subinterval and pretend that it's constant. And then we can use the fact that distance equals velocity times time. So we're going to look at an example. So here I've broken down the time into every 1 second intervals, and I've found the velocity given our equation v equals t squared. So 0 squared is 0, 1 squared is 1, 2 squared is 4, and 3 squared is 9. So what we're going to do is we're going to assume the speed over the first second, so from t equals 0 to t equals 1, is 1 meter per second, so the velocity at 1. Then we're going to assume that the speed over the second second, t equals 1 to t equals 2, as the velocity at 2, which was 4 meters per second. In the third second, t equals 2 to t equals 3, we're going to assume that it's 9 meters per second. So we know that it's not these velocities over the entire second interval, but we know that it's not going to be too far off. So we're just going to use this as an approximation. So our total distance would then be approximated by 1 times 1 plus 1 times 4 plus 1 times 9, which is 14. And we're multiplying each of our velocities by 1 because that is the length of our intervals, 1 second. So again, distance is velocity times time. So the time for each of them is 1, and the velocity is those velocities that we found at t equals 1, 2, and 3. Now there's nothing telling us that we had to use the higher of the speeds, right? The velocity at 1 for the interval 0 to 1, the velocity at 2 from the interval 1 to 2, and so on. We could have used the lesser of the speeds, which would have been the left endpoints. So the time from 0 to 1, we could have used the velocity at 0, which would have been 0. And the time from 1 to 2, we could have used the velocity at t equals 1, which is 1. And then the third second from 2 to 3, we could have used the velocity of 4, in which case our approximation would then be 1 times 0 plus 1 times 1 plus 1 times 4, which would be 5 meters. So this tells us that the distance traveled is somewhere between 5 meters and 14 meters. But we still don't have the exact distance traveled, right? It's just an approximation, somewhere between 5 and 14 meters. So the following is a graph of our velocity function, v of t equals t squared. So it looks like a parabola. Hopefully you've seen the equation f of x equals x squared. So it looks something like this. And I've drawn it from t equals 0 to t equals 3. The height of the function is the velocity. What we're going to do is we're going to show graphically what we just did on the last slide with our table. So we're going to approximate the velocity for the first second between 0 and 1 as 1 meter per second. So we're looking at that first table we did, the upper bounds. So graphically what we're doing is we're assuming the velocity from 0 to 1 is a constant 1. So it looks like this straight line here. And then for the second between 1 and 2, we were assuming the velocity was 4. So that is going to be represented by the next blue line. And then we assumed the third second from 2 to 3 that the velocity was 9, which gives us roughly this lovely line here. So you can see it a little better here. So that is the function we were approximating our velocity by. What we're going to do is we're going to connect these lines just straight down. So we have lovely rectangles. Recall again that distance is time times velocity. This is the same thing as finding the area of these rectangles, because again the height of the rectangle is the velocity. There you have the 1, the 4, the 9. And the width of each rectangle is 1. Right? 1 minus 0, 2 minus 1, 3 minus 2. And that was exactly our time interval. So the distance, which is time times velocity, is the same thing as the area of our rectangle, our length times width. And you can see here that the area is now shaded. So again, the distance is the area of the rectangles. Using subintervals of 1 second each isn't going to give us a terribly accurate approximation. Remember, depending on what velocity we chose for each of those seconds, we got both 5 meters and 14 meters. And that's kind of a big difference between those two. So the question is, how do we get a better approximation? Well, if we had tried every half second or every quarter of a second, it would give us a smaller time frame to be using that velocity approximation. So the smaller the subintervals we choose, the better an approximation to the total distance we'll get. The question is, what would these sums of this distance look like? So we know we'd be adding up a bunch of different products, right? The time times the velocity, plus the time times the velocity, plus the time times the velocity, and so on. So what we're going to do is we're going to let the intervals 0 to 3 be broken up into, say, n equal subintervals. And we're going to call those subintervals t sub 0 to t sub 1, where t sub 0 is 0, and then t sub 1 to t sub 2, t2 to t3, all the way up to tn minus 1 to tn, where tn is 3. Now that we have those, we're going to figure out what we're going to use as the velocity on each of those subintervals. So for simplicity's sake, we're going to use the right endpoint of each subinterval. So if we're looking at the interval from ti minus 1 to ti, then we'd be looking at the velocity at ti. So our sum is going to look like, again, the sum of products, velocity times time. So we've got here the distance equals the summation. So if you haven't seen that before, the capital sigma means the sum of. It means we're going to start at I equals 1, and we're going to end at I equals n. And what we're going to sum is the velocity at t sub I. So again, the right endpoint from t sub I minus 1 to ti. So here's our velocity. And then we're going to multiply it by delta t, where delta t is the length of each subinterval. So again, we've got the velocity times time is the distance. So delta t is the way we write the length of the subinterval. We also could have used the velocity at the left endpoint, so v of ti minus 1, or the midpoint, whatever the midpoint is for our subintervals, or really any value inside the subinterval. It's not going to matter, and we'll see why in a little bit. So what we're going to do is, again, we want to create smaller and smaller subintervals, or more and more subintervals. So we're going to let n go to infinity, which is the same thing as delta t, the size of each subinterval, going to 0. This will give us a better and better approximation of the distance traveled. And as n goes to infinity, we should theoretically, come up with the exact distance traveled. That is the limit, as n goes to infinity, of the summation of I equals 1 to n of the velocity at t sub I times delta t should give us the total distance traveled. This limit of sums is given a special name and special notation. So the limit of the sum is written as the integral from 0 to 3 v of t dt. This is called the definite integral. So again, it's the definite integral from 0 to 3 of v of t dt. So we're going to look at the similarities here. We have delta t on the left and dt on the right. So the limit as n goes to infinity of delta t we write as dt. And notice both of them have the velocity at t, which is good. And then the 0 to 3 with this squiggly kind of elongated s, that comes from the summation part. So summation, just like sigma, starts with an s. So the integral looks like an elongated s. And the 0 to 3 is just telling us what our bounds were. So if you remember, we were looking at the distance traveled from t equals 0 to t equals 3. So that's where this notation comes from. It comes directly from the limit of the sums. So next we're going to see what this looks like graphically. So we showed the first example where each subinterval was 1 second. So the following are representations using every half second and every quarter second. So if we notice our rectangles, which are our subintervals, the width of those are getting smaller, and the heights are getting closer and closer to the curve, which was our actual velocity function, t squared. So the question is, what happens if we do the same thing that we did with our summation? What happens as n goes to infinity? So as n gets larger and larger and larger, again, these rectangles are going to get skinnier and skinnier and skinnier, and the heights of these rectangles are going to get closer and closer to the actual curve, v of t equals t squared. So as we can see, the area of our rectangles actually becomes the exact area under the curve, v of t, from 0 to 3. So what does this tell us? Well, it tells us that the integral from 0 to 3 of v of t dt, which again is the limit as n goes to infinity of our sums of v of ti times delta t, equals the change in distance, which again was our whole goal, trying to find out how far the car went, which is also equal to the area under the curve of v of t from t equals 0 to t equals 3. But notice, we haven't actually figured out the exact distance yet. We still just have an approximation and a notation for the exact distance, but we haven't found a numerical value for the exact distance. If, however, we knew a function for the position of the function, usually denoted by s of t, then the total distance traveled from t equals 0 to t equals 3 would just be s of 3 minus s of 0, right? The position at 3 minus its starting position at 0. So if we put this all together, we get the change in distance is the definite integral from 0 to 3 of v of t dt, which is s of 3 minus s of 0, which would be really great if, again, we knew what s of t was. So the question is, how do we find s of t? Well, we know the velocity, right, t squared, and we know how velocity and position are related to each other, which is that the derivative of position, s prime of t, is equal to the velocity, v of t. This means that the integral from 0 to 3 of s prime of t dt, which again is v of t, is s of 3 minus s of 0. This is known as the fundamental theorem of calculus, It's the main overarching idea of calculus. And it's true for any function, not just a position function. So the function can be telling anything. It doesn't have to be doing, velocity of a car or the position of a car or anything like that. And in general, we write it as the integral from a to b of f prime of x dx equals f of b minus f of a. So again, this is true for any function. We're going to leave the actual finding of s of t, or again, in the general case, f of x, for our next class. So have a good day.